Bismillahirrahmanirrahim. For reasons that we have discussed, econometrics textbooks are thoroughly confused about the concept of causality. Now, there are two concepts which are extremely important in understanding what regression models are and how they function. And these are the concepts of autonomy and invariance. It will be our purpose in this lecture to explain what these mean. This cannot be done without an understanding of causality, and that is why existing discussions of these are very thoroughly confused. So, a brief history of econometrics. Econometrics was founded in the early 20th century and became standardized in the 1960s via the Cowles Commission approach. And basically, the Cowles Commission took the view that causal relationships are embodied in structural equations. So all of the equations that we put down are causal relationships. These are assumed in advance, a priori, before the start of modeling. The causality ideas are not explicit in the model. There is no notation, no language, mathematical or conceptual, to express causal assumptions. The idea was that some variables are exogenous, they are uncaused, and then there are endogenous variables. These are caused by the exogenous variables. So these are the basic fundamentals of the Cowles Commission approach, which was the dominant approach until the 1970s. In the 1970s, an oil shock caused all major forecasting regression models to fail by large amounts. So this led to an examination of the foundations of econometrics, and two major critiques came out of that. One of them was the Sims critique, that the causal assumptions made in regression models are false, and so what we need to do is just abandon causality and go to just a pure description of the data, and that is what Sims approach based on VAR modeling does. As opposed to this, Lucas' critique said that the causal assumptions are false because the regression models just depict the surface relationships, and we need to go deeper. We need to dig deeper into the causes of these relationships. Otherwise, when the causes change, the coefficients change, and this is what happened in the oil crisis. So these two are rather dramatically different analyses. Sim says we should abandon causes and go to pure description, and Lucas says that regression models fail because they are too descriptive. They just describe the patterns on the surface and they don't take into account the hidden causal factors. To understand this dispute and confusion, we have to use two key concepts. One is autonomy. An equation is autonomous if the whole world changes but the equation remains stable. So this equation functions independently. Like you see, if I drive a nail into the wall using a hammer, then the hammer is the cause of the nail going into the wall, and this will be true even if there is political upheavals and storms and lots of things are changing in the world. Of course, nothing is invariant to all things, but the second concept that we need is invariance. That is, the parameters of the equation remain stable when policy changes, or so for example, we have a consumption function. This is pretty stable relationship because income causes consumption, but in an oil shock, things available on the market might change, and so you might want to save more. So the relationship is there, but the coefficients might change. So the invariance refers to the stability of the parameters, but there is some ambiguity because sometimes it's also used to refer to the stability of the relationship itself. All this can be clarified only if we look through to the causal structures which are underneath the observation. Ragnar Frisch, who was one of the first founders of econometrics, talked about three types of relationships. One is the structural relationship, which we will call autonomous. These are the basic fundamental driving relationships within the data. Then there are what he called confluent relationships. These are valid relationships, but they change if the environment changes. And then there are spurious relationships, which are just correlations on the surface of the data, but there is no basis for them. So you can't rely on them to forecast. So nobody was able to understand these terms because they cannot be understood without causality, and so basically they dropped out of the language and the practice of econometrics. But once we have understanding of causal structures as developed in the previous lecture, then what we see is that a direct causal relationship is autonomous. If X causes Y directly, this represents a mechanism in the real world which links changes in X to changes in Y. This mechanism operates regardless of what else is going on in the world, and so that is what makes the relationship autonomous. It is not a relationship between the numbers of X and the numbers of Y. The autonomous nature comes from the fact that there is something in the real world which is linking the values of X to the value of Y. Now, if you have an indirect causal relationship, X causes Z, which causes Y, and we omit Z from the analysis, then this is a confluent relationship in the sense that it's not direct, so the relationship is a genuine one, but it is unstable. If the values of Z change, then the nature of the relationship between X and Y will change. So it's not stable to changes in the environment. Finally, a spurious relationship is caused by a common cause. So if Z causes Y and Z causes X, then because of the factor Z, X and Y will appear to move together, because when Z changes, both of them will change. But if you look at regression of X on Y or YX, neither one causes the other, and so this is an accidental correlation. There is confusion about invariance because it is used in both ways. The relationship between X and Y is invariant because it is stable, doesn't it get affected. So that's the idea of causality. But there is another way, and that's more common, that if we want to measure what is the quantitative effect of X on Y, the causal effect. And is this effect invariant or is it changing? Maybe if I change X, sometimes it causes Y to change a lot, sometimes it causes Y to change a little bit. In both cases, the causal relationship is there, but the impact, the magnitude, the size of the effect can change from time to time. So one meaning of invariance is if the size of the causal effect does not change. Now, if you think about it as follows, let Z1 and to Zn be environmental variables which are in our model, then Y depends on X by a linear relationship. Y is equal to A plus B times Z, but these numbers A and B, the relationship, can be affected by the environment. So A can be a function of the environmental variables, and B can also be a function of the environmental variables. So the B is actually the strength of the relationship between X and Y, and if B moves up, that means that the X gives a bigger hit, has a bigger causal effect, and if B moves down, X has a smaller causal effect. And this can be affected by the environmental variables. So the strength of the relationship can change even though the causal relationship remains the same. We get a regression model out of a causal relationship if we assume that only the constant A is affected by the environmental variables, and the B, the slope of the relationship, does not depend on Z. If that is the case, then we can sometimes write Y equals A of Z plus B times X. B is no longer a function of Z, and then A of Z can be written as A0 plus A1Z1 plus ... plus ANZN plus BX. So this now, in this regression relationship, the Z's and the X look like they are the same. If some of the Z's are not observed, then this becomes an error term. So in other terminology, z's are called covariates and the x is the regressor, because the causal relationship is between x and y and the z's are just modifying the strength of this relationship. But when you look at the regression, all of these variables look exactly the same. So there is a lot of confusion between what is a covariate and what is a regressor. To clarify the confusion, we have to separate two concepts. One is the causal relationship, x forward arrow y, and the other is the attempt to quantify the causal effect. So this we will write as y back arrow function of x and other variables. So when you have a causal relationship, this never denies the possibility of other causes. So when we say x is a cause of y, it's possible that there are many other causes, and it's even possible that there are mediating variables, that x is affecting y through some intermediate value which we don't know about. So that's why the quantification of the causal effect is much more difficult than assessing that there is a causal effect. And the strength of the causal effect will vary with environment, whereas the causal effect itself does not. So we will use some notation to try to keep these things clear. A forward arrow will always represent a causal relationship. A backward arrows we will usually use to mean a quantification of a causal relationship. So y back arrow a plus bx, we're not only trying to say that x causes y, but we're trying to say that b measures the effect, the size of the causal effect. But we also need to distinguish between causal factors and covariates. To see how we can do this, consider the relationship between education and earnings, which is very huge number of regressions have been run on it. And think of parental education. This is a covariate. Parental education doesn't directly enter into the relationship between person's education and his earnings. So the regression to measure causal effects can be written as earnings is back arrow a plus b times education. So a and b are the parameters in the regression relationship. They measure the strength of the relationship between education and earnings. Now these factors, the a and the b, this strength can be affected by the covariates, the parental education. So if the parental education is large, then the earnings will tend to be large regardless of whether or not the child is educated. So the constant A is affected by parental education. Similarly, B can also be affected by parental education. So in the regression, in order to get a regression model, we assume that B is not affected. So B of PRE is B, and A is affected, so that we replace A by A0 plus A1 times parental education. If we do that, then we get that earnings is A0 plus A1 times parental education plus B times education. And now parental education is a regressor just like education. So the difference between education, that education is a causal factor for earnings, and parental education is just something which modifies the strength. This is not visible in the regression. So this is a failing of our notation. So we suggest that we create a new notation, earning back arrow parentheses a plus parentheses b times square brackets edu. So now the a and the b are the parameters of the relationship, and these parameters a and b can be affected by other variables, which are not part of the causal relationship. So the square bracket on the edu says that this is a causal factor for earnings, and the parentheses just says that these are measures of the strength. So if we look at the diagram, earnings is caused by education, and then there are other causes. These are the z's, and the constant a is some additional effect on earnings based on other causal factors. But also the strength of the relationship between education and earnings could be modified by some environmental variables, which don't have to be causal factors at all. So the parameter b is a function of z, the other causes possibly, and also other environmental variables which may have to do with other factors affecting how education impacts on earnings. So this notation allows us to distinguish between measuring the size of the effect, causal factors, and environmental and other factors. Now, the problem that econometricians are trying to solve cannot be solved. Basically, for example, let's have a look at Mincers equation. This is one of the most fundamental equations in labor market economics, and this says that earnings is a function of education and other factors. And so one of the key and favorite questions in this literature is that there is some confounding. There is a hidden variable ability which affects education and a hidden variable ability which affects earnings. So the solution to that problem is to condition on ability. If we fix ability, then we can conditionally on ability, we can trace the relationship between earnings and education. So one ingenious method to do that was to look at twins and study their earnings and education. And there are other methods. And these methods solve the problem of causality. But the other problem, which is to find an equation which is stable, where the coefficients a and b don't change from time to time, this is the problem which econometricians try to solve. And this cannot be solved because a and b will naturally drift over time and space due to changing environment. Let me illustrate that by an example. Instead of thinking about how to find variables which will make the equation fit better, we have to think about the mechanism. How is it that education affects earnings? So let's look at a simple, very first, very primitive, basic mechanism. Many jobs require credentials. So thinking about the Pakistani context, let's oversimplify and say that there are government jobs which always require credentials. You have to have a degree to get a government job. Private sector, where people are more informal, they will take anybody who can do the job. And there is a third sector, informal sector, which absorbs all the leftover labor. And let's suppose that private sector wages are high, government wages are intermediate, and informal sector are the lowest wages. And let's suppose that even though the government wages are low, everyone who is educated wants to get a government job because of the benefits, the side benefits and the retirement benefits and the perks, which are very good in the government sector. In private sector, you're always at risk of being fired, even though the wages are higher. So suppose that we have 50 educated people and 150 uneducated people. All the 50 get the government sector job, and of the uneducated people, 75 get private sector jobs and 75 get informal sector jobs. Then suppose that the government sector is the average of private sector and informal. Then education will, in this model, it will seem that education has no effect on earnings because the average earning of the uneducated is the same as the government sector. So this is the problem, that looking at the observations may give a misleading picture unless you look at the causal mechanism. Now we can study this in terms of the notation suggested earlier. Earnings back arrow equals A plus B times education. The A and the B are the parameters which can depend on many factors, and education is a causal factor. So econometricians want to find ways to model A and B so as to make the equation stable. But there is no stable equation to be found. We expect these numbers to be shifting over time. So we're trying to find invariance, find stability in things which are not stable. We are trying to find stable coefficients, but coefficients are not stable. Where is the stability? The stability is in the mechanism. So we should study the mechanism. How does education affect earning? Study the structure of the labor market. What are the entry-level requirements for jobs? How is the pattern of jobs changing? How are in the job market? How are requirements for credentials changing over time? So these are the things which will remain stable over time. And these are the things which make relationships work over time. So focusing on finding stable coefficients is focusing on the wrong problem. All of these issues are manifestations of the failure of positivism. Positivism says that we can ignore the underlying reality and focus on the observations. One place to understand this better is the forecast competitions that were run by International Journal of Forecastings. These were M1, M2, and M3 forecasting competitions were run, and they were done as follows. They collected 10,000 time series of real-world data. Of these, they released 1,000 as training data, and then they asked for people to submit algorithms to forecast, and they would test them on the training data, and then these would be applied to the actual series to see which one works best to create the best forecast. So lots of people entered this competition, and they gave algorithms based on ARMA models and exponential smoothing and Kalman filter and many other methodologies for analyzing time series. So all of these were tested to see which one works better. And what were the results? Understanding that forecasts work when models capture the underlying causal mechanism leads us to understand that this competition would fail because we are not doing anything to assess the causal mechanism. And in fact, all of these series have different causal mechanisms because they come from different real-world contexts. So if we forecast without knowledge of causality, this is just like a crystal glass, you just a random guess. And this is exactly what happened. Nothing was learned from these competitions. Some methods work well in some series, other methods work well in other series. At different points in time, one method works well and then it stops working well. It's just completely random. After the 3 competitions, the whole idea was abandoned because nothing was being learned from these competitions, as we would expect. To give another example of how focusing on data instead of on the underlying real-world causal relationships leads to failure, we look at a very important relationship for business. When I advertise something, how much sales does this generate? So as an exercise in regression models, there is a econometrics website which gives data on sales and advertising for a dietary weight control product. And there are 3 articles which analyze this data set to fit regression models and to do forecasting with it. The question is there any point in running a regression of sales on advertising? The causality aspect seems clear. We do expect to see that if a product is advertised, its sales will increase. Now, as far as it comes to quantification, how is sales affected by advertising? The coefficients A and B are subject to a lot of different influences, and running a regression of sales on advertising basically says that the impact that advertising had on sales last year will be the same as the impact that advertising has on sales this year. Now we know that that's not true in advance because everything has changed in the environment. So when the environment changes, the coefficients A and B will change. I mean, what the competitors are doing, what the products are, what the consumers are, what their incomes are, everything is changing. So we can't expect these coefficients A and B to remain stable. So just to give an example of how regressions chase after the wrong things, this is one of the articles which was using this data. And basically it says that if you run a regression of sales on advertising, it doesn't fit very well. So then it adds lagged values. What if the past values of advertising also had an effect on the current values? Now, one of the factors of regression is that the more variables you add, the better fit you get. So by adding more and more variables, you get better and better fit. But these models are meaningless. This is not why. These don't explain, because there is no causal relationship being modeled here. The Harvard Business School has Marketing Analytics 2.0, which actually creates some of these models, and it explains how there are very complex effects, which means that you can't isolate one factor and study it, because there are many different channels of advertising and they all interact with each other. And so we need to study the whole complex of causal factors together. And if you study any one factor in isolation, you will get wrong and misleading regression factors, regression coefficients. So to summarize the basic lessons of this lecture, we start with a collection of variables, and what we are mainly interested in is the direct causal relationships, and these operate when everything else is changing. And we have discussed how we can discover these relationships and how we can define them. These are the autonomous relationships. The sequences of causal relationships are indirect chains, and these are called confluent relationships. We don't need to study them separately because they are just a build-up of simple direct causal relationships. Finally, the most important category, which is the appearance of a relationship that happens due to a common cause. X and Y are both caused by the same variable z, so they appear to be related, but they are not. There is no causal relationship. Vast amounts of econometrics studies these spurious relationships. So apart from mixing up causal factors and covariates, there are two problems of regression analysis can be explained as: we are studying relationships y equals a plus bx when there is no causal relationship, so there is nothing to actually look for in such a relationship. The second is that there is a causal relationship, but we are trying to fit a regression which assumes constant a and constant b, when in fact these two constants are constantly fluctuating and they depend on other variables, and this dependence is not being studied. And why we fail? Because we are looking at the data only, and we are not looking at the real world mechanism which drives the causal relationship. Just as we illustrated in the case of earnings in the labor market, you can make progress by looking at how education affects earnings. You cannot make it by studying by doing data analysis on different kinds of variables.